Hey there, chemists. In this lesson, we're going to look at what buffers are and how they resist changes in pH. The reason they do that is because buffers, by definition, are a mixture. Specifically, they're a mixture of a weak acid and its conjugate, or it could be a weak base and its conjugate. But it's got to be something weak. And the idea you'll see is that it reacts with things that are strong because it itself is made up of something weak, and it turns the strong thing into a weak thing. And that's conceptually how the pH changes are resisted. They're very important. They're found in your own circulatory system as a way of preventing drastic changes in pH. The change in pH is very significant in biological systems, so most organisms have something in place that prevents that from happening. Here's an example of a buffer mixture. We have a half a molar acetic acid and a half a molar of its conjugate, sodium acetate. Sodium acetate is just the acetate anion. This is a salt, but the sodium ion isn't doing anything, so I can think of this as just acetate anion with acetic acid. In fact, it's easier to just write them as their generic expression, HA for the acid and A minus for the base, and I'm going to do that a lot when we write out our problems for today. So first of all, how do we get the pH of this solution? Well, they give us the Ka. If you're ever stuck, look at what Ka they give you, write the equilibrium that goes with that. This is the acid equilibrium. So we have Ha dissociating into an H plus and an A minus. Now we have 0.5 molar of the HA. So I have 0.5 molar. I'm going to lose some amount of it, let's say X. I'm going to gain X of the H plus, and yes, I'm going to gain X of the A minus, but I actually already have 0.5 of it in my starting point, and I'm going to gain some more of the H plus as this dissociates. So when I set up my Ka expression, Ka is 1.8 times 10 to the negative 5. That's equal to X times 0.5 plus X all over 0.5 minus X. And I could expand this and solve a big quadratic, but let's think first and then do the math. Ka is small, so I don't know how much this is dissociating, but it's probably not much. So compared to 0.5, that minus X is probably negligible. In fact, the plus X is probably also negligible. So we can get rid of both of those X's that are inside the parentheses, and this just becomes X. So that is my molarity of H plus. X is 1.8 times 10 to the negative 5 molar H plus. And if you want a pH, you just take the negative log. I'm just going to write what pH equals. When you take the negative log of 1.8, 10 minus 5, you get 4.74. So that's just how you calculate the pH of a mixture. We're doing the same thing we did before for weak acids, using the Ka that goes with the equilibrium. We just now have multiple starting points that lose and gain some unknown amount of X. It actually becomes easier because of these cancelings of those X's. And then you get a nice linear equation to solve. If they weren't 1-to-1, then I would still have numerical values here, but it'd still be a very easy linear expression to solve. Okay, so that's just how you calculate the original pH. Let's talk concept. How does this actually act as a buffer? What actually happens? Well, let's think about what were to happen if I had this mixture and I added strong acid. If you add strong acid, that's like adding H plus. And both of the things in the buffer will see that. The buffer is made of acetic acid and acetate, and H plus is going to react with the basic part of the buffer. So the acetate ion, C2H3O2 negative, is going to react with that strong acid, and it'll react fairly irreversibly because the acid itself is strong. That just means it makes more of the other part of the buffer. In other words, it turns the strong acid into a weak acid. And the same thing happens if you add strong base. Add strong base. Strong base would be hydroxide. This time, the hydroxide, since it's basic, will react with the acidic part of the buffer. The buffer has both parts to it, and whichever part needs to step up will, depending on what gets added. So acetic acid can react with hydroxide. You'll make acetate, and also a water molecule just to balance it. But the point is, the buffer converts strong into weak. And weak things simply don't change the pH as much. It changes a little, but not nearly as much as it would change if we added strong acid or strong base to some aqueous mixture that didn't already contain a buffer mixture. That's it. That's how buffers work, and that's what they do. So let's go one step further and actually calculate what happens when you do this change with some specific amount. Let's say I have this same buffer. These, by the way, are just abbreviations of acetic acid. If you see that HOAC, it's the same thing as that formula right there. I'm just going to write it as HA, a generic monoprotic weak acid. We have a liter of it with half a molar each, and we're adding some sodium hydroxide. Let's figure out what happens. Well, we're adding 0.01 moles of sodium hydroxide, aka hydroxide. So conceptually what's happening, it reacts with the acidic part of the buffer. That means we have 0.01 moles less HA, because it will react, as we saw up here. The base will react with the acidic part. It also forms more of the basic part. So we will have 0.01 moles more of the conjugate base of the A minus. That's just because acid-base reactions are 1-to-1. So our new starting point, if we write the equilibrium, HA, equilibrium H plus, A minus. Originally, we had 0.5 and 0.5 of each of these things, but now I have only 0.49 of the acid and 0.51. We have a little bit less of the acidic part and a little bit more of the basic part, but I'm going to solve for the pH the same way we did in the very first problem by now knowing what this looks like as it equilibrates. Let's assume it still loses X. It gains X of the H plus, and it gains X more of the A minus. It's the same Ka value. Ka goes with the acid, so that didn't change. So 1.8 10 negative 5 is equal to X times 0.51 plus X all over 0.49 minus X. K is small, so the plus X and the minus X get to be negligible. So this simplifies not just to X, but the ratio of 0.51 over 0.49 times X. And I can solve for X. It's 1.7 times 10 to the minus 5, just a little bit smaller than that. That's a molarity of H plus, because we defined it as that. And then to get the pH, you just take the negative log of that, you plug that in, you get 4.76. So it changed compared to where it was in the beginning. It's close, not very different, but close, and it makes sense. It's a little more, it's a little less acidic, a little more basic. So let's make a note of that. More basic. And that makes sense because we added hydroxide. we added a little hydroxide, it better get a little more basic. But it's a buffer, so it shouldn't change too much. Obviously, if we added a lot more of the hydroxide, you would consume all of one part of your buffer or the other, and then you're not in a buffer anymore. It can't handle that much. But if it handles, if you throw at it small amounts of a strong species, it can do that. Okay, let me interrupt and show you a special buffer equation known as the Henderson-Hasselbalch equation, which is just a more useful expression sometimes that chemists use to solve for the pH of buffer mixtures. So here we have some acid. I don't even know what lactic acid looks like, or I do, but maybe we don't. It's just some monoprotic acid and its conjugate base. So it is just HA and A minus. Don't ever be fooled by the names and formulas of more complicated looking molecules. You can always abbreviate them as things and apply the concepts you've learned earlier. So the equilibrium is always HA dissociates into an H plus and an A minus for a monoprotic acid. And we know that Ka is, I'm going to write the expression, bracket H plus, bracket A minus, all over bracket HA. And I intentionally left some space there because I'm going to take the negative logarithm of the Ka, and I'm actually going to take the negative logarithm of that big expression on the right as well. And if I do that, I can get some mathematical things out of this. The negative logarithm of the Ka, that's also known as the power of Ka, or the pKa. The negative log of this big quotient, well, is the negative log of this big quotient, but I'm going to factor out the H plus and call this the negative log of H plus. And then if you remember your rules for logarithms, when you have one thing times the rest, you get to add them as logarithms. So this will become minus the log of the conjugate base all over the original acid. And I'm simply going to rearrange that equation and solve for the negative logarithm of H plus. The negative logarithm of H plus, that's also known as pH. This is pH. So pH is equal to pKa, and then let's move this term to the other side, and then you get the following equation. pH is equal to pKa plus the logarithm of the concentration of the base over the acid in the conjugate pair. This is the Henderson-Hasselbalch equation. I am going to call it the buffer equation to remind me that I can only use this when we're in a buffer. You can only use this when you're in a buffer. You have to have an appreciable amount of each part of the buffer in order for this to work. So I can use this directly to plug in my values that I have for this 0.25 molar of A minus and 0.75 for the lactic acid, and they give me the Ka value. So there's the Ka value. So the pH is the pKa. That's the negative log of this number. I'll just write that. Negative log 1.4 times 10 to the negative 4 plus log of the ratio of the molarities. A minus is the basic part, 0.25. HA is the acidic part. Go back and look, it's 0.75. So that's just the log of a third. You plug all that in one calculation, you get your pH. So it's just a little faster because we're often given molarities anyway. In fact, sometimes you're given pKa instead of Ka, but it's easy enough to calculate. This again is only when you're in a buffer. I'll actually make one modification because it's sometimes useful. Maybe make a note to this yourself. You can also, in addition to using the ratio of the molarities, you can also use the moles of each component as a ratio. And you should be able to understand why that's true. The ratio of the molarities in a given mixture, the volume is the same. So how do I turn moles into molarity? You divide each by volume. It's the same volume. So the mole ratio of the conjugate pair is the molarity ratio. And depending on which one they give you, it just might be easier. I don't often see this written in the buffer equation, but I think it's a lot more useful when you start to look at some problems that you do. All right, let's try a couple of questions here. In fact, let's see if we could use this buffer equation to make our lives easier and solve for things. First up, find the pH of a 0.25 molar ammonia and 0.4 molar ammonium chloride species. So the ammonia, that's a weak base. Ammonium is its conjugate acid. Notice they give me the Kb of ammonia. So if I write the buffer equation, pH equals pKa plus the log of the concentration of the base, which is the ammonia, all over the concentration of the acidic part, the ammonium. I have everything I need. The pH, the pKa is the negative log of the Ka. I have a Kb, but we can get that. Remember that Ka is simply Kw divided by Kb. And I'm going to put this all in the same expression, plus the log of the ratio of the molarities. It's base 0.25 all over the acid 0.40. One calculation. You plug that in, you get a pH of 9.05. Makes sense. It's basic. Usually buffers that are made of a weak base and some of their conjugate have a basic pH. Not always, but that's pretty common. When you have a weak base in its conjugate, it's usually a basic buffer, as opposed to a weak acid in its conjugate. That's usually an acidic buffer. It depends on the molarities, though. All right, how do we use the buffer equation to solve for what happens after you add some acid? I'm going to rewrite the same equation, pH equals pKa, plus the log of the ammonia over the ammonium. But here I'm actually going to take a page from what we just set up above about using moles instead. Let's actually change those to mole values, and you'll see why. The moles of ammonia over the moles of ammonium. And let's start to plug some numbers in. The pH, same as what we did in the previous part, because K is the same. Negative log of whatever 10 to the negative 14 divided by 1.8 10 minus 5 is. I'm not even calculating it as a separate thing. You could. Plus the log of, all right, now let's get smart. What's true about the amounts of moles of each species? Well, it's in a liter. We initially had 0.25 molar of a liter, so 0.25 moles of ammonia, and 0.4 moles of ammonium. We originally had 0.25 of ammonia and 0.4 of ammonium, but we're adding a tenth of a mole of acid. So we're going to have that much less of the basic part and an identical amount more of the acidic part, because that's what that's going to react with. So we have less of the base and more of the acid. And I can put that right in the same expression. This is just the stoichiometry buried in the ratio. So now I've got my equation. I just plug in all the numbers. You get 8.74. And it makes sense. It is slightly more acidic. We had 9.05 a moment ago, and now we're a little bit more acidic, a little bit lower on the pH scale. So we can very usefully use this buffer equation, not just to get the pH in the beginning, but even to bury all the little changes that happen, as long as we keep track of what's going on when we're adding things like an acid versus a base. Okay, just to wrap up, we said in the beginning that buffers resist changes in pH, but only up to a certain capacity. You need to have a significant amount of each part of the buffer in order to make it a good buffer. And the best buffer capacity occurs when that's true, when your moles of acid is roughly equal to your moles of base, Or alternatively, you could say the concentration of the acidic part is roughly equal to the concentration of the basic part. That's just your best buffer capacity. So think about the buffer equation for a second. Let me go back up to that buffer equation. If I have an equal mixture of each part of the conjugate pair, this becomes the logarithm of 1. And the log of 1 is 0. So your best buffer is when the pH is equal to the pKa. And we'll see this again in titration problems when we do that in our next and final acids-bases lesson. So the pKa is actually equal to the pH in your maximum buffer capacity. So how do we pick buffers? Well, it's based on the parent acid when we're picking buffers because it's the Ka value that tells you. So if I want a buffer of 4.3, then I need a pKa to be roughly equal to 4.3. And if we approximate what the pKa is for each of these, remember the pKa is just the negative logarithm of the Ka. And we could even plug it into some of these values. The first one, if I take the negative logarithm of that number, I get 2.87. If I check the second one, I get 4.89. Third one, 4.19. And the last one, 7.46. We want a buffer that's pretty close to 4.3. The number that seems closest is certainly this benzoic acid. That's your best choice. I don't think I'd be able to do that very easily without a calculator. Certainly looks like those two are closest. I could probably eliminate the first and the fourth choice, but I would need a calculator, I think, to really hone in on the fact that benzoic acid is the best choice. Speaking of doing calculations with logarithms and without a calculator, let's just talk about that for one quick second at the end here. Let's say you have to take the negative log of 6.4 times 10 to the negative 5 and just make a rough approximation of that without a calculator. You should know that the absolute value of the exponent in the power of 10 is what it's close to. So obviously it's close to 5. You can still feel comfortable by knowing that. But is the negative logarithm of 6.4 10 minus 5, is that going to be a little bit less than 5 or a little bit greater than 5? That's key. Are we 5 point something or are we 4 point something? Well, think about what negative log of just 1 times 10 to the negative 5 is. The negative log of 1 times 10 to the negative 5 is exactly equal to 5. And if I make this number bigger, I'm taking the negative logarithm of an even bigger number. So your negative logarithm is actually going to get smaller as a result. So the negative log of something times 10 to the negative 5 is actually going to be equal to 4 point something, as certainly was the case when we looked at this. In fact, this is closer to 10 minus 6. This is closer to 10 minus 4, isn't it, than 10 minus 5, which is why the actual value is closer to 4, which means we actually could have done this with a calculator. The negative log of 1.3 10 minus 5 would be closer to 5. The negative log of 6.4 10 minus 5, you're more than halfway there through the logarithm scale, would be closer to 4. So benzoic acid is the best choice without a calculator. Okay, that's how we deal with buffers and how they resist changes in pH.